So last time we covered the concepts for, doping, intrinsic, extrinsic semiconductors. So a quick question here: what are these concepts? PP, NP, NN, PN. What are they? And NI. What are these things? What is this first?
Concentration of gold and P-type silicon.
Yep. Is everybody getting that? The concentration of holes in a P-type silicon semiconductor. This one? In the P-type semiconductor, the concentration of electrons in the N-type semiconductor, concentration of holes in the N-type semiconductor. The last one, you want to check a couple of boxes. So what are they for the concept of this little symbol here? So first, this is the concentration of electrons and holes. In where? Intrinsic silicon. Per what? Per cubic centimeter. And then what? At room temperature. But that's specifically just for room temp, Ni. But this is at a certain temperature, actually. So I was wrong last time. So this should be at a certain temperature. You can have multiple different Ni's, depends on different temperatures. So at room temperature, it's going to be 1.5 times 10 to the 10th per cubic centimeter. But Ni, if I'm just saying Ni, it is at a certain temperature. And when it's a room temp, okay. Moving forward with the semiconductor basics. So first of all, you need to know there's a concept called drift currents. This is a piece of silicon and the holes. If you apply a voltage here, the holes will be pushed in that direction because the holes hold positive charges and electrons are going to flow in this direction. This is a piece of silicon. And this is called the drift current. Keep in mind that all the drift currents are driven by electric field. Because you add a battery here, it's going to apply an electric field at the two terminals of the piece of silicon. So the hose is going to flow in that direction. Electrons are going to flow in the opposite direction. Okay, and V drift, because all these charges are flowing, and there will be a specific velocity associated with this type of behavior. So V P drift, so the speed of the hose equals to the mobility of the hose times the electric field intensity. This is mobility. It's the intensity of the electric field. Similarly, the electrons, the drifting electrons velocity is mu n times E. right? And next, you should understand that mu n is larger than mu p. And what does that mean in your mind? Just think. It depends on the electric field, right? So electrons are more active, more mobile. How to say that? So the mobility of the electrons are just higher than the mobility of the holes. Okay. Moves easier under the same electric field intensity. Mm-hmm. And next, resistivity of the piece of silicon equals to 1 over Q times mu n times n plus mu p times p. So this is the mobility of the electrons, concentration of the electrons, mobility of the holes, concentration of the holes. And this is the magnitude of electron charge. Do you remember what is that value from physics? Yeah, it is 1.6 times 10 to the minus 19. What's the unit? Coulomb. That's the amount of charge an electron can carry. This much Coulomb. And this is called resistivity. Yeah, one interesting I didn't cover yesterday from the lab. It's a different concept. I mean, it's metal. This does not apply to metal. So if you have a piece of metal like the rod, a rod, wire, you have been using in the electronics labs, metal wire, right? So what's the resistance? Or it can be a resistive material, doesn't matter. It's just a piece of material, okay? So resistance is the resistivity times L over A. So L is the length, right? Here's L. And A is a cross-sectional area. Which is this circular shape. So A equals to pi r square. So that's the resistance of this piece of material. It's a rod material. And for the N well, it's different. So the N well is being doped into the substrate, and the N well's shape is not a rod. It's like something like this. Not sure if I can draw it. Very bad at drawing. Right? No, let me do this. That making sense? So for example, this is N well being doped into the P substrate, and this is the length. Ignore this. So this is the length of the N well, and what is this parameter here? The depth, right? Which you don't actually care about because you cannot change it. If it's a specific foundry process, they cannot change the depth. It's going to dope specific depth of the N well into the P substrate. So what is this parameter here? That's the width of the of the N well. So does this theory apply to this material or this shape? Yes, right? So the resistance of the N well is actually the same, can be described using the same theory. But the A here is a little bit different, right? So it's going to be L over D times W, or W times D, and which is rho times L over W times 1 over D. Probably going to swap this to here. So this is a specific ratio, right? You only care about the ratio here, but not the one single value, because whenever L changes, if you change W at the same time, it's not changing the resistance, since D is not changing. That making sense? Rho is not changing, it's the same material, and 1 over D is not changing because it's just one specific foundering process. It's not being changed at all. So the only parameters here are L and W. If you keep L and W change in the same rate, then you are not changing the resistance. That's why we have a concept called sheet resistance. Sheet resistance. It can be applied to both the N well and also some other resistive materials we are going to use in the future in this class. The polysilicon, the same material as a gate, can be used as a resistor as well. But this is the N well resistor, and this is the concept of sheet resistance, which means that every single square, it is 800 ohms. Doesn't matter how big the square is, right? But you have to follow the rules for the C5 technology. It cannot be too small, because the doping machine cannot dope that tiny feature onto the P substrate. You have to follow the feature. I think the minimum feature or the minimum size of the N well is 12 lambda, if I remember correctly. 12 lambda. 12 lambda. Every lambda is 300 nanometers. So 12 lambda is 12 times 300 nanometers. It's the smallest size of the N well. So it can be this. If you times 2 to both the width and length, you have a square N well, piece of N well like this has the same resistance. Because, well, L times 2, W also times 2. It's not changing the resistance, right? But here is a different concept. This is a resistivity for the silicon semiconductor. It's a different equation. And according to that, there's another concept called conductivity. Sigma equals to 1 over rho, right? Just whatever here, Q times mu n times n plus mu p times p. Right. Let's look at one example here. Given P equals to N equals to Ni equals to 1.5 times 10 to the 10th per cubic centimeter, and mu N is 1350 square centimeter per volt per second, times second. That's a unit for mobility for the electron. And mu P equals to 480. And the question is, what is rho, the resistivity of this piece of material? Cannot be easier, right? Rho equals to 1 over Q times mu N times N plus mu P times P. And what is Q? It's 1 10 to the minus 19 Coulomb, right? Just plug in all the numbers you can calculate for this guy. And what's the unit for this guy? It is ohms times centimeter. It's being used here in the semiconductor scale. But in general, in electrical engineering, in general, the resistivity unit is actually ohms meter, ohm meter. Voltage times second. Is that voltage times second? Yeah. Mm-hmm. Let's look at the second example. A p-type semiconductor and Na equals to 10 to the 16th per cubic centimeter, and mu n equals 1110, and mu p equals 400. What is the resistivity? That's the resistivity, and this is a constant. And this is given, this is given. And you need the concentration of electrons and holes. You don't have it now. You only have this guy. P-type, then Na is huge. Is that making sense? Does that make sense? For the p-type semiconductor, you have a large Na. What is Na? Yes, the concentration of donor, no, the concentration of acceptor atoms, right? And it's the same value as the concentration of holes after it's been doped. So Na equals to what? Is that correct? Huh? Acceptor. The concentration of the acceptor atoms is the same as the concentration of the holes. So it's going to be what? P what? Should that be PP? It's a P-type, right? So definitely no, it's going to be a P here. And because the concentration of the acceptors is the same as concentration of the holes, so it should be a P here. And which is 10 to the 16th per cubic centimeter. And you know PP times what equals Ni square? And why? NT, right? It's the same material, still a P-type, with concentration of the electrons. So in that case, you can calculate for NP, which is Ni squared over PP, which is 1.5 times 10 to the 10th over 10 to the 16th. Wait, is that correct? Square, right? Forgot this. Which is 2.25 times 10 to the 20th over 10 to the 16th, which will be 2.25 times 10 to the 4th. What's the unit? Per cubic centimeter, right? Same example we covered in analog. trying to give you a quick review. I'm pretty sure you have forgot it. And then move forward with pin junctions, if you're ready. Ready for this? It's being recorded, so never mind. I'm going to give you the quiz at, give you 20 minutes, which means 10:45, right? 10:45. 10 minutes left. Pin junctions. I want to give you a review on pin junctions because I'm going to cover PNPs and NPNs, which are BGTs. If you forgot what are pin junctions, you cannot understand NPNs, PNPs. So pin junction is a diode. You put a p-type semiconductor with a n-type semiconductor, and it forms a pin junction. And because the p-type semiconductor has more holes compared to the n-type semiconductor, and the n-type semiconductor has more electrons compared to the p-type, so because of the concentration gradient, the holes is going to diffuse toward the n-type piece of the junction, and the electrons are going to diffuse toward the p-type of the junction. So it's going to form a, because the electrons come over to here to fill up the holes, and it's going to form a negatively charged area. And the same concept of the holes migrate to this part, and it's going to neutralize the electrons and form a positively charged area. Okay, and this region is called the depletion region. And here's a quick question. Is the p-type, I'm not talking about whatever in the middle, because apparently this part of the depletion region is positively charged. I already told you. It's not neutral. It's not electrically neutral. This part is negatively charged, right? It's not neutral. What about here? Is it neutral or charged? And here, why is neutral? I don't know. It's hard to explain it, but we have to think about in one specific way, so we can understand it intuitively. It's not equal to what? It is equilibrium, but it's just you know. So if you have a piece of silicon not doped yet, right? So you have that piece of silicon, it is neutral, which is understandable. And you have phosphorus, it's also neutral. And you put them together, it should be neutral as well. Even though you have more freely moving holes, but it's still neutral. It's hard to think about it, understand it intuitively, but you just think about it in this way. You have two neutral stuff, you put it together, it's still neutral. So these two areas are electrically neutral. All right. At one moment, you have, for example, you have two pieces of these different types of semiconductors, and put them together, and because of the concentration gradient, so the charges will start moving to the other side, and it's going to form these two areas, and because this is plus, this is minus, there will be a electric field formed by this depletion region. So before this electric field is formed, you can see that the positive charges are moving to the right and the negative charges are moving to the left. So what's the current direction? Right. Because the direction of the current is the direction of the positive charges. So here's the direction of the current. But however, after it forms a electric field, is a plus minus like this. The original current is flowing in this direction. The electric field is against that movement, right? So it's gonna push or slowing down that kind of movement. So after a few moments, equilibrium will be achieved, and it's going to stop at the specific thickness. It doesn't mean it's not moving anymore. So the charges are still moving, but they are just moving at the same rate, being driven by the electric field and being driven by the concentration gradient. When the equilibrium is achieved, right? So the rate or the speed that the charges moving to the right equals to the charges moving to the left. So it's going to stop at the specific thickness. Okay. And the current being driven by the electric field is called ID or IS. IS. It's called drifting current. And in the future, if you apply voltage to the two terminals of the diode, any current flows in that direction is called IS. So what's the direction of IS? What's the direction of IS? So because right now it's not being biased. So the diode is a diode. It just forms a little electric field inside, right? To the left. It's the current driven by the electric field is IS. Like this, right? Going to the left. So this will be IS. So drifting current. Here's the electric field. Plus minus. Left. Right? And the current driven by the concentration gradient is called ID, is a diffusion current. And even though you have a voltage applied to the diode, any current flows in that direction is also denoted as ID. So if I have nothing, I have no voltage applied to the diode, IS equals to ID at equilibrium. Right, that's everything you need to know. And one more thing, I left over here. The little E of the diode is called the building voltage or barrier voltage. E here, the little E here over the depletion region is called the barrier, or sometimes it's being written as VB. So it's a building voltage. Or barrier voltage. For silicon, it's normally 0.6 to 0.9 volts. or 0.9 volts at room temp. Any questions if we do the quiz? Hmm? ID is a diffusion current.